Thanks, Sepp. Hello. I want to tell you about I want to tell you about a simple and powerful way of generating all kinds of data. This is work with all my great colleagues, Aaron, Karen, Lasse, Sander, Ivo, Oriol, Alex, and Corey. So a standard approach for both modeling a distribution, learning a distribution in sequences, and to generate these kind of sequences, is to factorize this distribution P of x into a chain of small conditional factors. And these factors are conditional distributions over the parts that make the sequence. And this has been standard for many years in sequence modeling, is what underlies LSTMs and RNN sequence models for text and so on. Now we can take this equation and trivially generalize it to multidimensional data. We can generalize it to images where the factorization then involves two products, one across the rows, one across the columns of the image. There's also channels, but let's not worry about that at the moment. We can also factor across other tensors, like interesting tensors such as videos. Now, this factorization is trivial and simple in its mathematical form, but a question arises, what kind of architectures do we need to be able to model these efficiently, quickly, and actually obtain powerful samples and also powerful results? So recently, we had these questions with a number of my colleagues, and over the past year, we worked on a few models, on the Pixel RNN, Pixel CNN model for images, on its extension to videos, and on the Byton model, which is a different architectures a new architecture for text prediction, and on the wavelet model for audio generation. And in this talk, I would like to highlight a few of these things. I will not go through all of that. I will just highlight a few of the important aspects of these models. And it's a unifying family of generative models. We, of course, rely on a lot of great prior work, and here's a subset of it. So let me begin with an architecture for sequence prediction. So when we think about RNNs, and we think about very long sequences, if the sequence is very long, we have to process it in a serial fashion, right? And of course, we can try to use we can cut the backpropagation through time and make it shorter and so on. But the serial aspect is core to RNNs, and it's very hard to get around it. Now, because we were interested in very long sequences, in long sentences made of characters, or long sequences in the audio waveform made of lots of samples, 16,000 samples per second. Because of the reason we were pressed to find a parallelizable architecture, something that could at least during training, that could be parallelized across the entire sequence. So of course we thought about convolutional networks, but convolutional networks have a slow-growing receptive field unless one does something to them, and this something is introduce a dilation factor in its kernels. This has been done for image segmentation before. We did this for one-dimensional sequences. And so what happens, we use these convolutions, which are masked or causal in the sense that they see only the past and don't see the future. We apply it to our one-dimensional sequence. We apply it layer by layer, and we double the dilation factor in each of these layers. What results from this is an exponentially growing receptive field, exponential in the numbers of layers of the network. And so with just a small number, dozens of layers, or 24, 36, in principle, one can get the receptive fields of 1 billion tokens or so on. So besides this advantage, we can actually inspect how forward and backward signals flow in these architectures. And we can compare it with the normal flow in deep RNNs. What we see is that because of this structure, with just a few steps, the signals can reach all these steps in the past. And that is without making pooling assumptions or combining combining the input signals or other things like this. So we naturally get a kind of memory which in RNNs, it's at every step, it's limited in the sense that it has to remember everything from the past that is going to be useful for the future. Whereas in these convolutional networks, the higher we go in the stack, the fewer things these things need to remember, and they can specialize for the prediction at that time step. So these are nice ideas, but we have to benchmark it properly. And one of the common benchmarks for where LSTMs are kings to this day, and all kinds of refined, interesting, powerful models are the state of the art, is the Wikipedia text, state, character, language modeling benchmark. And we see that our simple approach was able to reach the best results on this benchmark currently. And the results coming out basically once a week. We also applied, of course, this architecture to the text-to-speech task and for audio generation. And we also obtained very good results, and this was done by colleagues Aaron and Sander. So this is our one-dimensional fast architecture for sequence modeling. I want to describe one modification of this architecture, which in a very simple way also allows us to model machine translation, the generation of these machine translation sequences. This modification is almost trivial, it's very simple. If we had the bytecode decoder on top, now we take a bytecode encoder, which is just as before, but now we do not mask the convolutions. We let the receptive field grow just as fast, and we simply stack the encoder on top of the decoder. This actually generalizes the sequence-to-sequence LSTM in the sense that it sidesteps the bottleneck and actually preserves the complete resolution of the signal. The way we make this applicable to variable length outputs is simply by letting the decoder, the top orange part, choose its own end of sentence token. We can train in such a way that basically, if it needs to go beyond the source representation, just does that. If it wants to be shorter, it can stop earlier. So not only we go around the bottleneck problem in these encoder-decoder RNNs, we also go around the quadratic factor in the normal machine translation models that use attentional pooling. So this simple architecture is actually linear time. How does it work? We have some recent results, and on this data set it works pretty well. And also it works comparably well to word-level LSTMs on other benchmarks too. Another really interesting feature and a really compelling aspect of the attentional pooling mechanisms is that they learn these very nice maps of how source and target words align. Well, these kind of architectures can learn these sensitivities automatically, implicitly inside the data. Now, I've spoken about one-dimensional sequences, and now I want to show you how we generalize these frameworks, basically the same architectures, but into multiple dimensions. Another very important problem in generative modeling, of course, is the modeling of video data. And so that means that once you have a sequence of past frames, we want to produce the future frames. We actually do not want to produce a single trajectory in general. We actually want to produce multiple trajectories because the world has this stochasticity in it. So we have to model these multiple trajectories. A single one could be sufficient for some applications, but in general, we want to have a generic model that can produce distributions across multiple possible futures. Again, the product rule, the dependency chain rule, tells us how to factorize this joint likelihood over all these pixels in the tensor data for videos into a sequence of conditional probabilities. And we have to be careful so that when we predict each single pixel in each frame, we condition it on both the spatial dependencies within that frame, that means the rows and columns within the frame, as well as the temporal dependencies in the past. And we have to do this properly across the three channels. A great innovation to do this properly and do this efficiently is the idea of mask convolution, which appears in pixel RNNs and pixel CNNs. And basically, just like before, we're masking the convolutions in the ByteNet and WaveNet models to not see the future. Now we mask the convolutions in order to not see the bottom and right of our image. And we generate from top, we generate simply, we choose one direction, we generate from the top left to the bottom right corner. So this is how the architecture of video pixel nets works. In orange, we see the networks that encode the context, each one frame at a time. And in this, and the one important thing about these CNN encoders is that they have to be resolution preserving. Just like before, we were preserving the resolution of the encoding in the translation model, and we were losing the least information. Here, in the same way, we preserve information for each pixel in the encoders. And what this allows us is to channel all the representational power of the network for the prediction of each pixel in the decoders. And the decoders are pixel CNN decoders. And the main difference is that in the decoders we have mask convolutions, and in the decoders we don't have mask convolutions, we have normal convolutions. Similarly, here we can use dilation in the encoders for very large images if you want to grow receptive fields fast with very few layers. A core idea that we developed when we're working on these models is a discretization of continuous values, continuous valued variables. This discretization is crucial both in pixel RNNs, pixel CNNs, in video pixel nets, and in WaveNet. A simple way to do this is, in the case of pixels, is just treat each pixel intensity as its own category and obtain these highly arbitrarily multimodal distributions using a simple softmax. This is for each pixel. This is important for robust learning and actually yields better results, quantifiably better results in likelihoods. So we took the video pixel nets and we decided to benchmark them. It's important to benchmark generative models, and one of these benchmarks is moving MNIST. It's a simple benchmark where you have 10 frames of MNIST digits moving and bouncing between walls. It was introduced by Srivastava et al. In 2015. What we see is that the VPN obtains 87.6 value for the density, for the entropy of the density. And this actually is basically just a hair above of the actual lower bound, which is, in this case is non-zero and can be computed very easily. The results in likelihoods, or in this case in the density, often and basically always correlate with the quality of the sample. This is true in basically everything I've told you so far. And this is why when we optimize these networks, we always try to push down the likelihood as much as we can, and we actually get qualitatively improved samples. What we see here in the left side, we see the 10 history frames. The right side, we see the 10 future frames. The bottom is the ground truth. The top is the baseline model, which doesn't have spatial dependencies, and we see blurring artifacts. The middle column, the middle row, on the other hand, is the production of VPN. And there is no blurring because it captures the spatial dependencies. Sometimes there is slight deformation, and that is the 1.3 nuts that we're missing. This happens again on another sample, in this case 9 and 4s. Similarly here. All kinds of artifacts have occurred generally with all kinds of video prediction models. We can also let this roll and just basically see how these generate. Again, on the left we have the model without spatial dependencies, and the right we have the VPN, and we see the blurring effects of the model without spatial dependencies and the non-blurring effects of VPN. We can also try a different data set. This is the robotic pushing data set. This is available online. What is nice about here is that each of these frames shows 4 continuation. To the left in the case of the model without spatial dependencies, to the right in the case of VPN, 4 continuation which start from the same history. We have a history of 2 frames and we predict 18 frames. And we see that because it's probabilistic, because it captures stochasticity, we have a plausible variation of continuations for the robotic arm moving around. Also, we predict about 18 frames. In other cases, we predicted more frames as well in other data sets, and this actually works pretty well for VPN. Another example of the variability of data set, here is just more motions of this kind. These are uniform samples, and there's no cherry picking actually. So this is it. This was my talk. So we described, pixel byte wavenets are a unifying framework for generating data. And they have similar architectural principles, and they work extremely well across different modalities. So let's use them, let's push the likelihoods up as much as possible. Thanks.
Nal, thanks a lot. Are there any questions?
I know your wave network really well, and with other kind of things that you talk about here. One very specific question here is that you talk about this quantization, the need to have quantization, that actually dramatically increased the size, the number of output numbers. Why can you simply do the regression just to get continuous numbers out? So the need for quantization, that's my question.
Yeah, so it's possible to use continuous distributions as well. For example, a recent paper by Tim Salimans and others in OpenAI, they still discretize the values, but they actually use a mixture of logistics, and you can see the details, and that is perfectly fine. In the case of pixels, we only have 256 outputs, so actually using the SoftMax is extremely robust and it's just as fast, so there's no problem with speed there. The bottleneck will be actually in the network, will not be in the sampling procedure. If your space is very large, other continuous distributions are good. Yeah.
So for wave that, the paper said that without quantization, nothing works.
Right.
I don't understand why.
So, well, the problem is if you use an L2 loss or something like this, right? You do not capture these. You basically have this blurring effect, right? That you have in other models, right? And the same happens for audio data, right? So you can use other distributions there probably as well, continuous distribution in the case of awareness as well probably, but the discretization helps a lot, right? To make sure that we don't blur stuff, right? Yeah, we don't take the mean, but we actually choose the modes. Yeah.
Autoregressive models like these ones seem to give really nice results, but their kind of inherently sequential nature seems to make them much slower to sample from than some of these alternative latent variable approaches like variational autoencoders or GANs. So do you have any thoughts about how you could push these kinds of models to get closer to kind of real-time generation?
So the theoretical bound is obviously fast. If you can sample, if you properly implement it, we can probably get very fast sampling speeds, right? So it's a question of course, there will always be a bound. If we want to generate 4K video, it's going to be probably pretty hard. But I think we can do much more than what we're doing right now, most likely. Yeah.
Yep. You say that the lower bound is pretty good to compute, and I just read the formula actually. But this lower bound is actually made over the assumption of a 3D model. I mean, 2D model plus time, right? So basically, this is the lower bound for a model such as the one you're presenting here. However, other type of model could actually have an even lower bound than that, couldn't it?
No, actually that's false. That's the theoretical lower bound. If you could see, if you had a oracle about what is coming next, and that is because of the way that the loss is formulated. It's actually a simple fact about the loss. You can see details in the paper. Yep.
I have a question. So my question is about learning representations. Like images are naturally not sequential data, right? So there's a two-dimensional topology to them. So do you think you can use this? I mean, at the end of the day, if the goal is learning representations, is this somewhere hidden under the hood of this, this powerful generative model?
So your question is whether the lack of a two-dimensional topology is a problem, or?
Problem not in image generation. I mean, the results are very impressive, but in learning representations. So
for learning representations? You mean for learning a single latent representation for the image?
Not a single. I mean, at the end, you want to learn about images, right?
Yeah.
That's the goal.
Well, yeah, sure. So there's a lot of latent representations in these models.
Yeah, I understand.
And they're also extremely sensitive to conditioning. So if you condition to a single vector, one thing we've done in our conditional pixel CNN paper, you can actually learn smaller representations if you want a single vector representation. Then you can do the usual averaging of the latents and things like this to get nice effects. But there's a lot of hidden representations in these models, so it's a matter of using them properly, I suppose. But yeah.
So have you looked at it? So in terms of what are those latent variables are?
No, we have not. You should do it.
I have another question for you over there.
Yeah.
In the tutorial on Monday, Goodfellow stressed that GANs maybe don't reach the optimal likelihood value, but that images generated are visually very appealing. What is your opinion on this?
I think I answered the question during the talk. No, so yeah, so I think GANs are a really great model, and I think that they are the least understood generative model at the moment. And as more analysis comes in, we understand better exactly what these models are capturing. And of course, there's a sense in which they capture just one or just a small number of modes of the actual distribution, and that's why the images look good, but only in that particular mode. But this analysis is preliminary, but there are results in the direction. We actually care about capturing entire natural distribution. And I think this is actually really important, unless you want to do simpler things. But if you want to do planning and things like this, capturing the whole distribution, I think it's important.
Thanks.
Okay. I have a quick question, actually. So, did you try also using it for like classifications? I only see like generation here, but did you try this on like say ImageNet or something like that to see how well it classifies?
So we have not done this.
Okay.
And it's similar to the question of the other guy. You should do it.
Okay.
You guys can work together.
Okay.
So very quick.
Last question.
Yeah, so for GAN style of generative model, one can actually put condition on there as the labels to allow the model to do classification or semi-supervised learning, etc. I wonder whether in your generative models discussed here, whether that allows you to do, maybe sequential classification if you condition on the labels.
I see. So you want to invert? Oh yes. So yeah, we have not tried this, but you can classify by using base rule. Basically, you can invert the. Is that what you mean?
Yes.
Or okay, yeah. We have not done this. Sure, you can do this. Yeah.
Okay.
Of course, the likelihood values are they're very sensitive, so it's going to be hard. It's going to be harder than the discriminative model, almost certainly, but it can be tried.
Okay, great. Thank you.
Now, thanks again. Let's thank the speaker.